Okay, so the next section that we're going to take a look at is a very important concept in not just chemistry, but biology as well. And that's that's the concept of buffers. So you really can't have a thorough discussion of acids and bases without also discussing buffers. So we'll define what a buffer is, and then we'll take a look at some of the calculations involved in making buffers and how buffers actually function. So a buffer solution can be thought of as a solution that keeps the pH. So buffer solutions keep the pH of a solution relatively constant when small amounts of acids or bases are added to that solution, right? So in other words, what buffers do is they resist drastic changes in pH. Now, buffers are important because you can imagine there are several situations where keeping the pH of a solution is critical, or keeping the pH constant of a solution is critical. So for example, blood, the pH of blood needs to be kept at a relatively constant level. The pH of your stomach needs to be, stabilized as well. And there are different buffers that work in each of these examples. Now, what is a buffer composed of? Well, typically, buffers are made up of a weak acid and its conjugate base. Okay, so right away, we know that we can't use strong acids like hydrochloric acid, nitric acid, etc. We need a weak acid, and we also need its conjugate base. And the conjugate base of a weak acid is going to come in a salt form. So sometimes you'll see the phrase, or the salt of its conjugate base. And that's because you can't just have the conjugate base ion floating around. It comes with a positive ion to neutralize its charge. So the salt here of its conjugate base. Okay, so weak acid and the salt of its conjugate base, that's the most common way buffers are made. We can also make buffers by using weak bases and the salt of its conjugate acid as well. So either way, we can make a buffer. The most frequent way, the most common way is the initial way, which is the weak acid and the salt of its conjugate base. So for example, if you have a system like our acetic acid system, which we've mentioned previously, so the two components of a buffer are critical in terms of how they actually operate. So in our buffer system, acetic acid that we have here on the left side, and then we also have the conjugate base of it, which is the acetate ion. Okay, so let me just write these out. This is acetic acid, and this is the acetate ion. All right, and this system, this is the equilibrium system. We have the two components that are necessary. So why do we need each of those components in a buffer? Well, if we added, this first example here is if we were to add, let's say a strong base like sodium hydroxide, right? Sodium hydroxide will dissociate completely to give us the hydroxide, and then we get the sodium ion. This is the thing that makes sodium hydroxide a strong base. So the acid component of the buffer is able to react with that hydroxide ion. And when it reacts with the hydroxide ion, the acid gives up its H plus to the OH minus, we make water, and then we end up making the acetate ion, which is the conjugate base. Okay, and if you think about what just happened here, this hydroxide is a very strong base, whereas the acetate ion is a much weaker base in comparison. So what happens is this buffer is able, this component of the buffer, the acid component of the buffer, actually converts a strong base to a much weaker one. And as a result, the pH of the solution does not change drastically. Yes, the pH will increase, but it will increase very minimally compared to if we didn't have something to neutralize this acid this base, the strong base that was added. Similarly, so what we've done here is we've traded, in other words, a strong base for a weak one. Right, the hydroxide for the acetate ion. And as a result, the pH change is minimized. Similarly, if you were to add, if we added a strong acid like HCl, right, this is going to dissociate completely to give us H plus and the Cl minus, right? The H plus is what makes it a strong acid. Well, what component of the buffer will react with this? Well, it's then going to be the conjugate base part of the buffer, right? So the CH3 COO minus can react with that H plus to give us now back the original acetic acid. So what has happened here? Well, something similar has happened. We've traded a strong, right? This is a strong acid for acetic acid, which is a weaker one. By comparison, right? So the conjugate base part of the buffer is able to then react with any added acid, convert that strong acid into a much weaker one, and as a result, the pH change is minimized, right? It's not that the pH is not going to change, it will, but it will be much smaller compared to if we didn't have the buffer there in the first place. Right? That's generally how the different components of the buffer are going to work, right? We're trading, the buffer allows us to trade a strong acid that we've added to the solution for a weaker one. Similarly, the buffer allows us to trade a strong base that we've added to the solution for a weaker one. In both cases, the change to the pH is minimized drastically. Let's see how we can calculate the pH of a buffer solution. So it says calculate the pH buffer, that is 1 molar acetic acid and 1 molar sodium acetate. All right, so we can write out our equation, our acetic acid reversibly to form the proton, and then we also get the acetate ion. We have the concentrations here, the acetic acid, and then also the sodium acetate. We have our ice table set up, right, at equilibrium. We can assume here again, x is small. We solve for x and we find that x there is equal to 1.8 times 10 to the -5. So the pH of this is going to be 4.74. Right, so that's just a normal pH. Calculating normal pH as we've done previously using the ice table and the Ka expression. Now, what if we had that same buffer system, but we've added, let's say we add 0.1 moles of hydrochloric acid, right? So we're adding now 0.10 moles of HCl to this solution. We have a total volume of 1 liter of this solution. Okay, so then the concentration of the HCl that we've added would be 0.10 moles per liter. So that's 0.1 molar HCl. Okay, and that would also be the concentration of the H plus as well, right? Because it dissociates completely. So we have the H plus that we're adding to the system. Well, what happens when we add H plus to it? Well, as we saw previously, when we add H plus to the system, it's the conjugate base that reacts with the H plus, right? So we can write an equation, write a new equation for that addition. So we have our conjugate base component of the buffer will react with the H plus to produce the acetic acid. Okay, and how much do we have to begin with? Well, originally, okay, we have some of the we have 1.0 moles of the acetate, we have 1.0 moles of the acetic acid, and then we're adding 0.10 moles of this thing. So what happens as this reaction proceeds? Well, this system, then as we add the H plus to it, it will use up, it forces the equilibrium or forces this reaction to the left. So we're going to use up all of the H plus. So none of this is going to be left here at the end. This then is going to react in a stoichiometric ratio with this. So we have the 1.0 minus, because it has to react with all of the H plus. So that's going to give us 0.9 moles. And then we're going to make now, as these two things react together, we're going to make more of the CH3OH. How much are we going to make? We're going to make the same amount of the H plus that we added. So we're going to add here now 0.10. So that's going to give us 1.1 moles of the product. Okay, so this is what we have after here. After the added H plus has been consumed. So this is a two-step process that you think about. Okay, when you add the acid, how is that going to affect the buffer? Which part of the buffer system will react with it? Well, the conjugate base will react. It will use up, it will neutralize all of that acid that we've added. And as a result, their amounts will change, right? Based on the stoichiometry. So this is then what we're going to insert into our new ice table. So we have our CH3, COH now reversibly to form our H plus and our CH3OO minus. We can insert these values. So our CH3O minus is 0.9 molar. Let's color code these. That's in orange. Our H plus here is going to be nothing. And then the acid here was 1.1 that we calculated. All right, and we do the same rinse and repeat for our ice table. The change there would be minus X on the reactant side, plus X on the product side. And then at equilibrium, right, we have our equilibrium concentrations. We can substitute into our Ka expression. All right, so Ka products over reactants, we're again assuming X is small. Okay, so we end up with 1.8 times 10 to the negative 5, which is the Ka for acetic acid, is equal to X times 0.9 divided by 1.1. Okay, we solve for X. X equals 3.6 times 10 to the negative 5. X here is the concentration of the H plus. So then the pH would be the negative log of that, which would give us a pH of 4.66. Okay, so what we've noticed here is that the pH did change, right? It started off as 4.74, but it became more acidic, went down to 4.66, but it didn't change by a lot, right? So the pH of that solution was, the change to the pH was minimized due to having that buffer present. There's only a change of 0.08 in the pH units. If by comparison, okay, if we did the same thing, if we added the same amount of HCl to just pure water, the pH would change from, the pH of pure water is 7, it would change all the way down to 1. Right, so it'll be a much more drastic change, right? 6 pH units. If we did the same thing to an unbuffered pure water solution compared to this buffered solution here. So you can see the dramatic here, the change in pH is only, what is that, 0.08 pH units. Here for pure water, the change in pH would be 6. Remember, the pH scale is a log scale. It's a logarithmic scale, right? So a pH change of 6 is actually a 10 to the 6. That's 1,000,000 times difference in concentration compared to a 10 to the 0.08 change in the concentration. So a very, very dramatic effect here of what a buffer has to the pH of a solution when we add small amounts of acids, in this case, to it.